Welcome to Lecture 30, in which we will talk about an idea called Deutsch's problem. And the idea behind Deutsch's problem is the following. We are given that f of x is a Boolean function of the Boolean variable x. So in other words, x can be 0 or 1. And the question that we want to consider is this. So question, or maybe I'll call it problem, since this is Deutsch's problem. Problem. Does f of x have different values for, or maybe I should rephrase that, different output values for different inputs x, or does f of x always have the same output value regardless of the value of the input x. That's what we want to know. This is what we're trying to solve, and this will be the first algorithm that we've discussed in which we will see a clear advantage from quantum computing over classical computing. If we wanted to try to answer this kind of a problem classically, the only alternative would be to try the two different inputs values, x equals 0 and x equals 1, and to see if the output is the same or if it's different. But as we'll see with quantum computing, that's not necessary. So how does this go? Okay. Well, first of all, let's make the following observation. Associated with f of x, there is, and this is something we saw in chapter 6, there is an associated unitary transformation U sub f that acts as follows. So we have x and y coming in, and coming out we'll have x and y exclusive or f of x. Actually, maybe I should just make it like that. And all of these are cubits, so let me denote that as well. So this is the unitary transformation associated with the function f of x. And as long as we're at it, let's make an observation. Y exclusive OR with f of x is equal to y ANDed with f of x prime ORed with y prime ANDed with f of x. So if y equals 0, y exclusive OR f of x. If y is equal to 0, this first term would go away. Y prime is equal to 1, and so we would just get f of x. And on the other hand, if y is equal to 1, then the second term would go away because 1 prime is 0, and 0 ANDed with anything is 0. And here we would get 1 ANDed with f prime of x, which is f prime of x. So y exclusive OR f of x, in that case, would be f prime of x. So now that we've made these two observations, let's consider the following. Let's think about this unitary transformation acting on the state plus minus. Oh, and I guess I actually want to make one more observation up here above before we proceed. This picture, if this picture we have right up here at the top of the page, this could be written as UF acting on X, Y is equal to X, Y exclusive OR f of x. Okay, that's how we would write. This picture represents this equation. Okay, so now we have UF acting on the 2-qubit state plus minus. Well, to figure out what this is, let's observe that this is the same as UF acting on 1 over square root of 2, 0 plus 1. That's the plus qubit. And then the minus qubit is 1 over square root of 2, 0 minus 1. And so that is the same thing as UF acting on 1/2 and the 1/2 of course is coming from 1 over square root of 2 and 1 over square root of 2, and then we get 0, 0 minus 0 1 plus 1, 0 minus 1, 1. And so now we can pull out the 1/2, and this becomes then UF of 0, 0 minus UF 0, 1 plus UF 1, 0 minus UF 1, 1. Now let's remember the way that UF is defined up here. UF of x, y is equal to x, and then the second cubit will be y exclusive over f of x. And y exclusive over f of x down here is equal to f of x when y is 0, and it's equal to f prime of x when y is equal to 1. And of course, let me make sure you understand that by f prime of x here, I don't mean the derivative of f by any means. I just mean, remember, this is a Boolean function, so it has a value of 0 or 1. So when f of x is 0, f prime of x is 1. When f of x is 1, f prime of x is 0. I just mean the complement of f of x. Okay, so let's come down here and use that information to work on this a little bit. So the first one, again, UF of x, y, the first cubit of the result will be the same as the first cubit of the input. So we will have 0, and then the second cubit here will be 0 exclusive or f of 0. Now for the second one, we'll have, again, the first cubit is always the same, so 0, and then the second one will be 1 exclusive or f of 0. And then for the next one, we will have plus, again, the first cubit is always the same as the first cubit of the input, so we'll have 1. And then for the second cubit, we will have 0 exclusive or f of 1. And then finally, we have minus sign here, and 1. And then the second cubit will be 1 exclusive or f of 1. Now, what does this give us? Okay, remember, 0 exclusive or f of 0 will just be f of 0. So we'll have 0 f of 0 minus 0, and 1 exclusive or f of 0 would be f prime of 0. F prime of 0 plus 1, then similar to what we had before, 0 exclusive or f of 1 is f of 1. And then finally minus 1, and 1 exclusive or f of 1 here will be f prime of 1. And so that's what we'll have for UF of plus minus. Now, operate on the first qubit with H. Now, just to refresh your memory, and I hope that you remember this already, but I'll say recall, H of 0 is equal to 1 over square root of 2, 0 plus 1, and H of 1 is equal to 1 over square root of 2, 0 minus 1. So if we operate on the first qubit of UF, of this right here, of UF with plus minus, if we operate on the first qubit with H, then what will we get? Now, the second qubit, we're not bothering it at all. So you could write this as H plus I, meaning that we're going to operate on the first qubit with H, but leave the second qubit as it is. That operating on UF of plus minus, which is the term that we have identified right here. Okay, let's see what we will get. Well, in each case, we're going to get a 1 over square root of 2 out in front. So, and we already have a 1/2 here, so we get 1 over 2 times the square root of 2. 1 over 2 times the square root of 2. And now let's see all the terms that we will have. Okay, so when we operate on this 0 with H, then the result of this first term will be 0 F of 0 plus 1 F of 0. And when we operate on the first qubit of this term with H, okay, we'll have minus 0 F prime of 0 minus 1 F prime of 0. And now when we operate on this qubit with H, we will get plus 0 F of 1 and now remember that H of 1 has a minus sign here, so we'll get minus 1 F of 1, and then finally when we operate on this one with an H, and keep in mind it already has a minus sign out here, so we will get minus 0. Oh, and let's see, I think no, everything looks okay. Okay, so minus 0 F prime of 1. And then the minus will give us a plus, so we'll get plus 1 F prime of 1. So now let's go one more step with this. We'll get 1 over 2 square root of 2 and let's first of all group all the terms with having 0 as the first cubit. So we'll have 0 as the first cubit, and then the second cubit is we have f of 0 minus f prime of 0 right here from this term plus f of 1 that's from this term, and then minus f prime of 1 from this term. And those are all the terms having 0 as the first cubit. And then let's collect the terms having 1 as the first cubit. Okay, so we will have f of 0 minus f prime of 0 minus f of 1 plus f prime of 1. And now we make the following observation. If f of x has different values for, and again, let me be a little more, let's say output values. If f of x has different output values for different input values of x, by which I mean f of 0 is not equal to f of 1. If that's the case, then this term that we have just evaluated okay, so let's try to identify what this will be. Well, perhaps the easiest way to evaluate this situation is to make the following observation first. If f of 0 is not equal to f of 1, remember this is a Boolean function, it only has two possible values. So if f of 0 is not equal to f of 1, then f of 0 must be equal to f prime of 1. And similarly, f of 1 must be equal to f prime of 0. So, in this case, H cross I operating on U sub f of plus minus would be equal to 1 over 2 times the square root of 2, and let's see now what we'll get. Okay, we have 0, and then this will give us f. We'll keep f of 0 there. But now f prime of 0 we have identified as equal to f of 1 in this case, so we have minus f of 1 plus f of 1 minus an f prime of 1 we've identified as equal to f of 0. So minus f of 0 plus 1 times f of 0 minus f prime of 0 is f of 1 and then minus f of 1 and then finally plus f prime of 1, which is the same thing as f of 0. So plus f of 0. And if you look at that for a moment, you will realize that all the terms here in the first parentheses, we have plus f of 0, minus f of 0, plus f of 1, minus f of 1, so that all goes away, and we're left simply with 1 over 2 times the square root of 2 times 1, and then here in this parentheses we get f of 0 and f of 0, so 2f of 0 minus 2f of 1. So 2 and then f of 0 minus f of 1. And the 2 here will cancel with the 2 of 1/2 in front, and so we get 1, actually let's just write it maybe like this. We'll get 1 and then f of 0 minus f of 1 over square root of 2. And keep in mind now that f of 0 and f of 1 are not equal to each other. So this term here, which represents the second cubit of the output, is either 0 minus 1 over the square root of 2, or 1 minus 0 over the square root of 2. And so this final answer is plus or minus 1 minus. Again, if f of 0 is 0 and f of 1 is 1, and And keep in mind, if f of 0 were equal to 0, in this case that we're considering, then f of 1 would have to be 1, because we're considering the case where f of 0 and f of 1 are different. So if f of 0 is 0, and f of 1, therefore, is equal to 1, then this would be 0 minus 1 over square root of 2, which would be minus. So in that case, we would take the plus sign. And on the other hand, if f of 0 is 1, then that would mean f of 1 has to be 0. So we have 1 minus 0 over square root of 2. In that case, we would have minus 1 minus. So this is what we get in the case where f of 0 is not equal to f of 1. And now let's look at the other case. So let's say, on the other hand, if f of x is constant, i.e. f of 0 equals f of 1, then, well, in this case, then f prime of 0 would also be equal to f prime of 1. And therefore, h cross I, where h tensor product of I of uf of plus minus. Okay, in that case then, let's go back up here to our expression for that. Okay, we get 1 over 2 times the square root of 2, 1 over 2 square root of 2. And now we have f of 0, we'll have f of 0 minus f prime of 0, f of 0 minus f prime of 0, and then plus f of 1, but f of 1 is the same thing as f of 0, so plus f of 0, and then minus f prime of 1, but f prime of 1 is the same thing as f prime of 0, so minus f prime of 0. And then for the next part of it, we have f of 0 minus f prime of 0. The first two terms here are exactly the same as the first two terms in the first parentheses, so we'll just have f of 0 minus f prime of 0. But the next two terms are both reversed from what we have in the first parentheses. So if we do that down here, then we get minus f of 0 plus f prime of 0. And now, if we look at that carefully, we see that this time, everything in the second set of parentheses goes away. Here we have positive f of 0, negative f of 0, negative f prime of 0, positive f prime of 0. And so we would be left with 1 over 2 times the square root of 2, 0, and then in the second, the first parentheses, we have 2 times f of 0 minus 2 times f prime of 0. So 2 times f of 0 minus f prime of 0. And the 2's, the 1/2 here and the 2 will cancel, and so we'll be left with 0 and f of 0 minus f prime of 0 over square root of 2 and this will turn out to be plus or minus 0 minus. Again, we get the upper sign of plus if f of 0 is equal to 0. Obviously, if f of 0 is equal to 0, then f prime of 0 would be 1, and so we would have 0 minus 1 over the square root of 2, which is minus. On the other hand, if f of 0 is 1, then f prime of 0 would have to be 0, and we get 1 minus 0 over the square root of 2, which is minus. But this is the final answer in the case this is, again, when f of 0 is equal to f of 1, and here is our result when f of 0 is not equal to f of 1. So what does this mean? This means that now, if we measure, well, let's maybe say it like this. So, if we measure the first cubit with the standard basis, we will definitely measure 0 if f of 0 equals f of 1, and definitely measure 1 if f of 0 is not equal to f of 1. Of course, we don't have to worry about the plus or minus because that's just a global phase difference in both of these. So, or a global phase term. So, once again, if f of 0 is not equal to f of 1, we're in this case, and if we measure the first cubit with the standard basis, we would definitely measure 1. And on the other hand, if f of 0 is equal to f of 1, if f is a constant function, and we measure the first cubit with the standard basis, then we will definitely measure 0. And so with just one call to this unitary transformation, with just one call to that, inputting only that one input, plus minus, we have been able to determine whether the function f is a constant function or what they call a balanced function, meaning it's equal to 0 half the time and 1 half the time. Now, we don't know for what half of the time f is equal to 0 and for what half of the time is equal to 1, but we would know that it's not a constant function. So this is Deutsch's algorithm or Deutsch's problem, and it is our first example of how quantum computing can be used to arrive at an algorithm that is actually superior to the corresponding classical algorithm. So now I'd like for you to consider a problem on this topic. Having trouble now. So the problem that I would like you to consider is the following. So suppose that the input to UF is, now instead of the plus minus state that we had before, suppose that it is now plus and 1. The first qubit is plus, the second qubit is 1. Okay? I'm sorry, let's make that second qubit 0. Okay, first qubit is plus, second qubit is 0. And so if we apply the Hadamard or let's just put it into exactly the same terms that we have in the lecture. Let's just say if we apply H to the first qubit of the result, and what I mean by result is the result you get, i.e. the output from UF when the input is plus 0. That's what I mean by the result. So if we apply H to the first qubit of the result, and then measure the first qubit with the standard basis, what will we measure if F is a constant function? And the answers that we will consider are A, plus, B, minus, C, 0, and D, 1. And then 30.2 will say, same question, except now f of 0 is not equal to f of 1. And the choices here. Oh, okay. Let me add one more answer up here. I'll say a superposition of 0 and 1. I'm not going to specify what superposition, but we'll just say a superposition of 0 and 1. And on 30.2, we'll have exactly the same choices. Minus C 0, D is 1, and E would be a superposition of 0 and 1. That's not really, this is not E. I'm not wording that correctly. Let me say it this way. Let's say either, here we'll say it this way, possibly 0 and possibly 1. And same here, possibly 0 and possibly 1. But in all the other cases, it's definite. So let me, since I've had a little bit of hesitation in spelling out these alternatives for you, let's look at the problem one more time all together. So what we have here is we have an input to this unitary transformation, u sub f. And u sub f is just like we had in the lecture up here. Okay? And the only difference now is that in our lecture, as you can see right here, the input that we considered to u sub f is the 2-qubit state plus minus. But now, instead of looking at that input in our two problems, we're going to look at the input plus 0. Not plus minus, but plus 0. And so we're going to have that as input for u sub f, and then we'll get some output. And that output is what I'm referring to as the result. Now, if we apply h to the first qubit of this result, and then measure the first qubit with the standard basis, what will we measure if f is a constant function? Will we definitely measure plus, definitely measure minus, definitely measure 0, definitely measure 1, or will we be in a situation where we might measure 0 and we might also measure 1. And then 30.2 is exactly the same question, except in this case, we're considering what would happen if f of 0 is not equal to f of 1. And so now f is not a constant function. And again, if that were the case, and we did all of this, then what would we measure? Would we definitely measure plus, definitely measure minus, definitely measure 0, definitely measure 1, or might we be in a situation where we could possibly measure 0 and also possibly we might measure 1? Those are the two problems you need to consider for this lecture, and that is the end of this lecture. So, good luck.